This is section 8.8 improper integral part 2. Recall in proper integral we have two types. Type 1 is infinite intervals where it goes from finite number to infinity, or sometimes we have negative infinity to constant, or from negative infinity to positive infinity. So in these cases, we just replace the infinity or negative infinity with an arbitrary constant and take the limits that constant approach infinity. Okay. Now the second type of improper integral is discontinuous integrands. So what I mean is, when you look at the integral from 0 to 1 over x, so for example, it looks proper, right? It looks proper, nothing's wrong. But if examined a little bit closer, you would notice that the function here is not continuous at 0. Okay, so if you try to sketch the graph, and you probably see better actually. So if I sketch the graph, so here's an x-axis and here's the y-axis, right? The 1 over root x, right? So 1 over root x, the graph go like these. Okay, right? So here's 0 and here's 1. So again, the question here is really asking the area underneath the curve from 0 to 1, right? So here to here. Now you can see there's a bit issue here. See this gap because there's a vertical asymptote at 0. This is because at 0 the function is not defined, and at x approach 0 from the right it's go to infinity, so we have vertical asymptotes there. Again, with this improper integral, there are two types of answers. So either you got infinity or you got a finite numbers. For infinity, we say it is the integral diverges. If the answer is finite number, we call the functions or the integral converges to that number. Now, again, we cannot use the fundamental theorem of calculus here because at the lower end, lower limit is undefined, so you cannot plug in. So what we have to do is similar to what we did in type 1, is we're going to replace the 0. 0 is a problem here, right? It's an issue. We're going to replace the 0 with a arbitrary constant. Say a, right? So instead of going from 0 to 1, we're going from a to 1. We're looking at this area, right? From a to 1. Can we do that? Yes. Why not, right? So if we replace from a to 1, then I can certainly integrate and then do it normally, right? So once you have that, in order to value integral from 0 to 1, you just let your a, arbitrary constant a, he approach 0. Right? So as it getting closer and closer to 0, then you don't got this area here. Right? So you can see we have two steps. Step 1, replacing the lower limits in the case with arbitrary constant a, do it normally as a proper integral, then you take the limit a approach 0. Now in this particular case, when approach 0, since it's a one-side limit, this is approach 0 from the left. So it's only approach from the right, then you're going to see we will be dealing with right-hand limits in this case. Okay, so all right, so recap. In this case, we may have a finite interval, but the function may be unbounded somewhere on the interval. And in this case, it has a vertical asymptote at x equals 0. Okay, so with that said, step 1, we compute this integral from a to 1. All right, from a to 1. Then arbitrary a, so we can handle this, right? So we write the integrand at x to -1/2 power, x to -1/2 power. Then apply the power rule. If we add 1, it becomes x to the 1/2. We divide it by 1/2, or divided by 1/2 or times 2. So we have 2x to the half. From a to 1, plug 1 in. You have 2 times 1/2 is 2. And then plug a in. You have minus 2a to the 1/2 using the fundamental theorem of calculus. Now from there, we take the limit where a approaches 0. You see a approaches 0, or one that's approaches 0. With the plus signs there means coming from the right. It's right limits, right? So as you do that, basically I'm taking the limits of these quantity where 8 approach 0. So when 8 approach 0, let's go to 0. You have 2 minus 0 is 2. So our answer turned out to be 2. It's a finite number, and hence the area underneath the curve is precisely 2. And we say this integral converges to 2. Okay, 2 steps. Now, again, this is just one case of type 2. We might have case 2 where the functions, instead of discontinuous at the lower end, right, the left end point of the interval, it might be discontinuous on the right end point at 1, say, instead of at 0, or maybe somewhere in the middle, right? So we have 3 cases as well. So let's look at each case. Right, so case 1, if the function f is continuous on the interval from a to b, you see it's closed at a, open at b, so it is discontinuous at b. Is the upper limit not continuous there? Okay, so in this case we're going to replace the b. There's a typo here in this PowerPoint slide. We're going to replace the b with an arbitrary constant c. I call this c, right? So that's supposed to be c, right? Instead of from a to b, we go from a to c. Then we take the limit where c approach b from the left. Okay, so if we're going to illustrate this, it's going to be look something like this, right? So you have this x-axis, and then there's a y-axis, and now you have the interval from a. That's an a. So let's say he's an a. That's a b. And the function is not continuous at b. Or in other words, we will have a vertical asymptotes technically at b. So let's say it go like this, and the function is not continuous at b. Okay, so what we're gonna do, like from a to c. So we're just looking at this only, right? From a to c. I'll use the red color here. A to c. Okay, a to c. And then let's see approach b. Since it's going further to b on the left of b, so that's why I have the left hand limit. So that's the case 1. Okay, and then the case 2 is when we have the function not continuous at a at the low end. So at the low end, we can replace a with c. Again, that's supposed to be a c. Then when c approach a from the left, those are the example I just did. Actually, the example I just did a few moments ago. So we have that, right? And then let's say the graph this time is not continuous on the left side. So I'm assuming it takes places here. A. B. Right? So again, we're looking at the area actually over here and there. The problem is this kind of opens there, so that's what I can't do. So what we're going to do is we're going to replace this A with a constant C. So this is the arbitrary C is here. Right, so looking at it from C to B, looking at it, you see the B, and then let's C approach A from the right of A, so that's C approach A, right? Okay. The last case is when the function discontinuous at C, somewhere in the middle. If that happens, then you just split the integral into two, right, from A to B, and then, well, from A to C, then from C to B. So in that scenario, we will have, I'm going to do examples later, but these are the three cases, okay? Now look at this example. The integral from 0 to 1 dx over x. This is normally how it was written in the textbook, but the way it's, I don't like this notation, by the way. What I expect is an integral from 0 to 1. Clearly the dx should be in the back. Then if we put the x there, then what's left root 1. So I would like to write this way. Okay, say they're the same. So that way I can see the functions or the integrand is 1 over x. So the graph of 1 over x is like this, right? So it's actually is two branches hyperbola, right? So it's that's the x-axis, and then that is the y-axis. Okay. Now, of course, we only integrate from 0 to 1, so we're going to graph from 0 to 1 only. So if we take away other parts, then I have this, right? From 0 to 1. And we are looking at the area again between 0 and 1. This is the 1 is there. Okay. We're looking at this region. All right, so again, we do two steps. Step 1 is to replace where's the problem. The problem is at 0. See the function not continuous at 0. We have vertical asymptotes at 0. So we're going to replace the 0 with the replace the 0 with B. Actually, you can replace 0 with A or N. It doesn't matter, just a letter. Replace 0 with B in this case, and let B approach 0 from the right. Okay, so what happened is you would consider that here is B, right? So we consider this area. And then when we figure that out, we let b approach 0 and it approach 0 from the right. Now, then we have, this is the proper integral. Now we can do it. So antiderivative of x is natural log of x. So that becomes natural log of x from b to 1. Plug 1 in, plug b in. We have natural log of 1 minus natural log of b. Right, natural log of 1 minus natural log of b. Now from there, I can do, you know, what's natural log of 1? Or natural log 1 is 0, so that's equal 0. But as b approach 0 from the right, you might have to recall the graph of the natural log. The graph of the natural log is this. So as x approaches 0 from the right, you see that the natural log is actually getting smaller, smaller, actually larger, but in negative directions. So you end up with a negative infinity. Okay, so it's approach negative infinity. That approach negative infinity. Negative, negative, so it turned out to be a positive infinity. Right? So that's equal infinity. And in this case, we say this integral diverges. Okay, diverges. Now let's look at another example. Again, the integral is written a little bit weird, or at least I'm not comfortable writing in the integral like this. Instead, that should equal to or equivalent to 0 to 3 dx on the back. That means you have 1 on the top. So you have x minus 1 to the 2/3 power. So the first thing we do is look at this functions. 1 over x minus 1 to the 2/3. You can graph in the calculator to see what it looked like. But I can tell that this function is definitely not continuous at 1. At 1. And then a 1 is actually in between 0 and 3. So this is the case 3 of type 2 where the function is not continuous in the middle of the interval. Okay, so to do that, or we help you see that y, a not continuous one, you look at the graph from 0 to 3. At 1 we have a vertical asymptotes, right? We have vertical asymptotes. Okay, let me try to graph this. Okay, let me see, I need to redraw it. So it is there. Okay, see, not continuous at the interval from 0 to 3, and it's not continuous precisely at 1. So what we're going to do is we're going to kind of split that into two integrals naturally. You see that from 0 to 1 is one integral from 0 to 1. And then we go from 1 to 3, right? Same functions dx. Now what happened is then you're going to have this integral plus this integral. So that is the area on the left of 1 plus the area on the right of 1. Now when we do that, you see that the function not continuous 1 at the upper right upper limit, and on this second integral it's not continuous 1, which is the lower limit. So we handle these two the same as in case 1 in case 2. All right, so before we get there, it might be worth rewriting these functions, preparing for integrations. That's the same as x minus 1 to the negative 2/3, right? So in the denominator, it's raising the negative exponents, so they have a neat integral. Now from here, like we discussed, we will split this integral into 2, right? So, sorry. The first one, again, is from 0 to 1, and then the x minus 1 to the negative 2/3 dx. And then you're going to add the integral from 1 to 3 with the same functions. Then the first one, we will replace the 1 with a, say, b, and then that one, say, a. So we're going to replace the 1 with b, so that's from 0 to b, x minus 1 to negative 2/3, plus, now you have the integral from a to 3, x minus 1 to the negative 2/3, right? So from here, you can see, well, I could have step 1, but don't forget we have to take the limit here as the b approach 1. Okay, so your b is over here, right? So you see that it b approach 1 from the left. So from the left here, on this side, you got to take the limit. A is over here. A approach 1 from the right. Okay. So put it together. You're gonna have a limit b approach 1 from left 0 to b. This integrand. The other one I call c actually, and then c approach 1 from the right. Okay. Now, well, this integral is easy to integrate, right? Just add 1 to the exponent. So negative 2/3 plus 1 is 1/3. So you have x minus 1/3 divided by 1/3 or times 3. Same for the second integral. But then the first one is go from 0 to b. This one from c to 3. Okay. Then you plug in. After you plug in, you have 3 is b, right? B minus 1 to the 3rd minus 3 times 0 minus 1. See, 0 minus 1, so it can be negative 1 to the 3rd. Well, same thing for the second interval. Nothing fancy, but it goes from c to 3. So when you plug 3 in, that becomes a 2 to a 3rd there. And then you plug in c. That's what integral we got. Now going from here, let's check out. When b approach 1 from the left, that's approach 0, right? 1 minus 0, that approach 0. So what we left is negative 1 to the 3rd is negative 1 times negative 3. So that is positive 3 plus 3 times 2 to a 3rd. Okay, so 3 times 2 to a 3rd, or a cube root of 2. So in this case, the integral converges to 3 plus 3 cube root of 2. Okay. Now you can do these two examples the same, which I'm going to skip from 0 to 2. Don't forget that when you encounter improper integral, when you recognize the function not defined at the end, right, 0, the upper lower limit, then that's equivalent to replace 0 with a. So we're doing this and take the limit where a approach 0 from the right. Okay, this one, the function not continuous at 2, so that between 0 and 4. So that's, you have to split into two integrals from 0 to 2. 2 over x minus 2 plus from 2 to 4, 2 over x minus 2 dx. Right? So you split into 2, and each of these will be the improper integral. Okay. One last reminder, the improper integral of type 2 sometimes is not realized. Okay. So when you did something wrong, you don't even know. So make sure that you're going to do it carefully by showing the work properly. So let me show you this one quickly. Okay. If you look at this integral right here, let's see which one I want to say. The integral from 0 to 3 there, that's not the one I want to say. Might be, well, sorry, I don't have the example here, but just watch out for the improper integral. Sometimes you don't realize it is. Anyway, that finishes the last section of chapter 8.